So moving on from ethane, let's go to ethylene. So also has 2 carbons, but if you look at ethylene's formula, instead of 6 hydrogens, ethylene only has 4 hydrogens. So this was a pretty big mystery back 100 or 2 years ago when these compounds were being discovered, how it is that we can have 2 carbons but only 4 hydrogens now. So in order for carbon to keep its 4 valence electrons and for it to form its 4 bonds, we have to make a structure where the 2 carbons are double bonded together. So here we've got the 2 carbons in the center of the molecule. Each carbon has 2 hydrogens attached to it, and we then have a double bond. So we can indicate that double bond a couple of ways using these dot structures here. This shows the actual 4 electrons that are shared between the 2 carbons. So this time, if we can imagine the electrons that originally came from carbon, I can do those 4, for instance. The other carbon would have maybe originally had those ones like that. So one electron came in with each hydrogen, but then in order for the carbons to make the 4 bonds, it had to share 2 electrons from each carbon in order to make that double bond. So the double bond has 4 electrons now that are shared between the 2 carbons, and we can see that pretty clearly in the dot structure, but these 2 parallel lines here between the carbons means that it's a double bond and that there's 4 electrons being shared between there. We can tell carbon still has the 4 bonds that it needs if you count the actual lines that are attached to each carbon. 1, 2, 3, 4. Okay. So carbon is still fulfilling that 4 bond representation that we talked about before. So the structure of ethylene, though, its shape is much different than the structure of ethane. The bond angles in ethylene are about 120 degrees. So the structure right here is actually drawn pretty accurately in terms of bond angles. So 120 all around. That's going to be characteristic of this type of bond to carbon, as we'll see in a second. So not only is the bond angle different, but the whole shape, the overall shape of that molecule is different. It is a planar molecule. So all of its atoms exist in a single flat plane. If we look at one of these structures, this molecule could just sit down flat on the paper without anything sticking out towards you or anything going back behind you. From this side view, we could maybe draw it like 2 hydrogens are coming toward you and 2 are coming back, but it's still flat. It's still completely planar in its shape. So that's a big key difference between ethylene and ethane, like we were talking about. So let's talk about how it is that those bonds can arrange themselves with this 120-degree bond angle. Now, what we're going to form 3 hybrid orbitals this time instead of 4. With ethane and methane, we had an Sp3 hybridized carbon. Now I'm going to make an Sp2 hybridized carbon. So let's start out with carbon's 4 electrons. 1, 2, 3, 4. And you could pretend if one of these from S was promoted to a P or whatever. It doesn't really matter. But what happens is that now I'm going to mix together the central S orbital and 2 of the P orbitals, but I'm going to leave 1 P unhybridized. So there's going to remain a P orbital, and remember P orbitals have those 2 lobes, one up and one down, so that's going to stay behind, but then I'm going to make 3 new orbitals this time. So what will actually get formed are the 3 identical Sp2 hybrid orbitals, each with 1 electron, and then the unhybridized 2p orbital, hybridized. Right? So let's take a look at what that's going to look like. Right here is this unhybridized p orbital. It remains from the very beginning, from when carbon had originally 3 of those p orbitals. Now here's 1 that was left behind, that was unchanged in this hybridization process. So the 3 new orbitals, though, are called Sp2. because we took one s and we took two p orbitals altogether, and we now come up with 3 new hybrid orbitals. So the 3 hybrid orbitals, if we're looking at it this way, the 3 hybrid orbitals will be planar, sort of in this horizontal plane going across, and then the unhybridized p orbital will be perpendicular to it, so going above and below the plane. So if we look at it from the top, here we're looking down at the top of this p orbital. So the Sp2 hybridized orbitals are evenly spread on sort of the equator, sort of the midsection of this. And for them to be equally spread out, that's where this 120-degree bond angle came from. So the Sp2 hybridized orbitals, there's just 3 of them. They push away from each other as far as they can, and they form that 120-degree bond angle. These are the ones that are free to overlap with atoms in all the directions, the 3 directions around that carbon. These are the ones that will be first forming those sigma bonds, like we talked about. So 1 hybrid orbital from each will overlap to form a bond, just like in ethane. So if I have an electron in each of these hybrid orbitals overlapping with, for instance, a hydrogen for 2 of those and carbon. Yeah, let's draw that a little better. Overlap here with the carbon. Then that gives us those 120-degree bond angles that we referred to, but that doesn't account for the double bond yet. All I've shown here is overlapping that forms sigma bonds. So sigma, sigma, and sigma. Where am I going to find the extra electrons to overlap to make the double bond? Well, remember, we still have this unhybridized p orbital that will still contain 1 electron. So that unhybridized p orbital will actually be able to overlap with a p orbital on an atom that's next to it. But it has to have a p orbital just like this, and it has to be oriented in just the same direction. So what we form then, it's called a pi bond. Here I've got 2 Sp2 hybridized carbons, for instance. The Sp2 hybrid orbitals will overlap just like that to form the sigma bond. Okay. So remember, sigma goes straight from one nucleus to the other nucleus, right in between them by that overlap. And then what happens is these p orbitals will actually overlap. So if we imagine some overlap on the top lobe of that p orbital, as well as overlap on the bottom lobe of that p orbital. Here, let me make that blue stand out a little better. It's 1 electron from each hybrid orbital, right? That's what this dot is showing right here. Let's just make that into a arrow. So 1 up, 1 down, 1 up, 1 down. These 4 electrons right here are the 4 electrons that make up the double bond, right? So that means that this double bond consists of 1 sigma bond and 1 pi bond. So be careful here. Where this carbon-carbon double bond is, we can clearly see the sigma bond in between there that goes between those 2 carbons. The pi bond itself has 2 parts. So it's a common misconception to think that this is 2 pi bonds. We saw that in our Chem Activity 3 in class. This is 1 pi bond. 2 parts of it. Let me make that very clear that this is 1 pi bond. All together. So the top, this is half of a pi bond. On the bottom, that is half of a pi bond. All right, so looking at the structure of ethane, then, that's where that comes from. These hybrid orbitals that are sticking out on either side will overlap with the hydrogens. The carbons overlap with each other 2 ways to make the double bond. So sigma always happens first. If we need more electrons to be shared, we can add on a pi bond. So that's what we explain here. Sigma bonding only shares 2 electrons between 2 atoms. There's no way to do a sigma bond with any more than just a pair of electrons. If we need to share more electrons, we have to add pi bonds on top of those sigma bonds. But like we saw with the way that pi bonds work, that requires leaving one p orbital out of the hybridization. So we no longer can hybridize all 3 of those original p orbitals. We have to leave one out so that it's free to overlap with the p orbital from the next carbon to make this pi bond. So each additional pi bond adds 2 shared electrons, and pi bonds can only form by overlapping unhybridized p orbitals. Let me go to my webpage here. I have a 3-dimensional structure of ethylene. This is just like what we looked at. If we look at it from the side, you can see that it's planar. It's totally flat. All of these atoms are within the same plane. So nothing pokes up, nothing pokes down. So if I show you the Sp2 hybrid orbitals, those exist in between each of the atoms. So the carbons have those Sp2 hybrid orbitals. They overlap with the hydrogens to make the CH bonds. The carbons will overlap with each other to make a sigma bond in between them, okay? But that's only 2 electrons. To add in the other set of electrons for the double bonds, here I show you the unhybridized p orbitals, and I'm actually not showing you those overlapping just yet. What we can do is we can imagine that there is overlap happening between these 2 red ones on the bottom here, and then there's overlap happening between those 2 blue ones on the top there. So the combination of those 2 things overlap makes that one pi bond. So the double bond that's in here, 1 sigma bond, 1 pi bond. That's what we just said. 1 sigma bond, 1 pi bond is what makes a double bond. Carbon will be Sp2 hybridized even if it's double bonded to an element other than carbon, like something like oxygen. So let's consider formaldehyde for a second here. CH2O. So if I put a carbon in the middle, carbon and hydrogen can only make single bonds with each other. We saw before in bonding patterns that oxygen makes 2 bonds, and in order for carbon to make 4 bonds total, it has to double bond to that oxygen. So oxygen will have 2 lone pairs for it to have its octet, for it to have its 8 electrons around it. So if we look at this carbon has 3 bonding groups around it, or bonding domains like the Pogel book calls them. So these 3 bonding groups will be separated by equal 120-degree angles, or something very close. I mean, they're not identical bonds, so they won't all exactly be 120, but they'll be very close. This carbon will be Sp2 hybridized. So we can tell it's Sp2 hybridized because that's what makes that 120-degree bond angle, and carbon will bond with 3 atoms when it is Sp2 hybridized. Before, when carbon was Sp3 hybridized, it bonded with 4 atoms because we had 4 hybrid orbitals. Here we only have 3 hybrid orbitals, so that makes the CH bond, that makes the other CH bond. The sigma bond between the C and the O makes half of this. The other half of this double bond comes from a pi bond, just like we saw with ethylene. So I have a structure of formaldehyde right here. Here's the structure just like we have it. Sp2 hybrid orbitals make the sigma bonds. So there are also some Sp2 hybrid orbitals on oxygen, but we won't talk about those just yet. Unhybridized p orbitals will exist on the carbon and on the oxygen, so that the sigma bond makes half of that double bond. The pi bond, where we have overlapping on the top and overlapping on the bottom, makes up the other half of the double bond. So it actually turns out that oxygen will have 2 lone pairs that will be occupying its other Sp2 hybrid orbitals. So lone pairs can be in hybrid orbitals. That's fine. That's where they'll actually go here. So 2 electrons in that one, 2 electrons in that one. That's why that sort of arrangement there, that's why we typically draw the lone pairs spread out around an oxygen like that, where it's double bonded. So I've got one lone pair sort of up and left and the other pair sort of up and right. so that these 3 electron groups, lone pair, double bond, are spread out around the oxygen too. So whenever carbon makes this bonding pattern, it is sp2 hybridized. sp2 is what's going to allow us to make that one double bond to carbon.